Welcome back. Let's learn all about tangent vectors. Alright, so in the last lesson, you learned to find the derivative of a vector-valued function and how it represents the tangent vector of the plane or space curve at a particular value of the parameter t. And we really only focused on the derivative part of that, right? We really focused in on how do we find the derivative of vector-valued functions. We didn't really go into too much detail about what we can do with them. And so that's what I want to focus on in this video, specifically in regards to tangent vectors. And so to sort of get things started, I want to quickly look back to something we did in Calculus 1, because we're going to be able to do something very similar here in Calculus 3 for vector-valued functions. Remember that in Calculus 1, we could use the derivative to find the slope at a specific point on a function. Right, so for example, here I have a problem from Calculus 1 where you want to find the slope at a specific value of x on a function. We want to find the slope at x equals 2 on f of x equals x squared, and I have the graph of that function over here. When we're finding the slope at x equals 2, we are finding the slope at a specific point on this function, and we would call that point the point of tangency. And we can find that full point by plugging 2 into the function. That would give us the y value, and so you'd have the full coordinate point. If we do that here real quick, let's find the point of tangency. F of 2 is equal to 2 squared, which equals 4. So our point of tangency is the point 2 comma 4. So let's plot that over here. 2, 4 takes us right here along the curve. So that would be our point of tangency. That is the point 2, 4. And so we could find the slope at that point along this curve by using the derivative. So we could take the derivative of our function f of x, using the power rule for derivatives, f prime of x is equal to 2x. And so then evaluating that at 2 would give us the slope at x equals 2, or more specifically, the slope at that point of tangency. And so let's do that. F prime of 2 is equal to 2 times 2, which equals 4. So the slope at x equals 2, or the slope at this point of tangency on this function is 4. The tangent line at that point along the function has a slope of 4. Okay, so what we did here was nothing new, right? This is all stuff that we have done before in Calculus 1. But the reason I just went through this example is because we can do something very similar for vector functions. We're not going to be finding slope anymore, but when we do take the derivative of a vector function, what we get represents a tangent vector at a specific value of the parameter t, and so we could find a specific tangent vector for a specific value of t on a vector function. Okay, just like we can find a specific slope at a point along a function, we can find a specific tangent vector at a point along a vector function or a plane or space curve. And so let's take a look at an example of what I'm talking about here. And to keep it simple, we're just going to work with a 2D plane curve. We'll look at space curves a little bit later on. I just want to keep it simple to start. So let's begin with a vector function in 2 dimensions. So here's our example. We want to find the point of tangency and tangent vector at t equals 1. And our vector function r of t is equal to a vector with components of t squared and 2t. Okay, so the first thing I'm going to do here before we do anything regarding the point of tangency or the tangent vector is I want to draw a sketch of this plane curve. Now, this is not going to be necessary for you to complete this problem, but I do want to show you a visual of what's going on here and what we're finding when we find a tangent vector at a specific value of t. And so let's quickly sketch this plane curve. What we want to do is eliminate the parameter here. Remember that our x component is t squared and our y component is 2t. So our two parametric equations are x equals t squared and y equals 2t. So if we solve for t in this equation, we'll get t equals y divided by 2, and then we can plug that into this equation to eliminate the parameter t. So if we plug y divided by 2 in for t and square it, we will get x equals y squared divided by 4. All right, so that is the equation of our curve that we are working with here that is represented by this vector function. It is important to notice that there's no domain restriction here. We're working with all values of t, and both of our components here are defined for all values of t. There's no way that t squared or 2t can be undefined values. So we are working with the entire curve here, not just a section of it. And so let's plot this. This would be a parabola pointing in the positive x direction, since it's x equals positive y squared divided by 4, but the parabola will be stretched a little bit because we are dividing by 4. So just to get an idea of how we would plot this curve, if you plug in y equals 2, you get 2 squared divided by 4, which is 4 divided by 4, and that's 1. So a point on this curve would be a point where x equals 1 and y equals 2. All right, so going to our graph over here, if this is x equals 1 and this is y equals 2, that right there would be a point along our parabola. And so that should help us get the shape of this parabola correct, because we know it's going to be symmetrical about the x-axis. So we can just reflect that point to the other side, and then our parabola will look something like this. Okay? That would be our vector function r of t. And so now that we have graphed our vector function, let's work on finding the point of tangency and the tangent vector at t equals 1. And the point of tangency is going to be pretty easy. To find that point, we just have to plug t equals 1 into the vector function, and that will give us a vector whose terminal point is the point of tangency. All right, so for the point of tangency, we'll have r of 1 equals 1 squared, comma 2 times 1, which equals a vector with components of 1, comma 2. So the terminal point of that vector would be the point 1, comma 2, and so that would be our point of tangency. And so that's exactly the point we plotted earlier, this point right here. This is our point of tangency, or the point that we are looking at along this curve for the vector function where we want to find a tangent vector. All right, so that's where t equals 1. Now, we found the point of tangency, so let's work on finding the tangent vector. To do that, we first need to take the derivative of our vector function, because the derivative of a vector function does represent a tangent vector for a specific value of t. Once we have that derivative, we can then plug in t equals 1, and that will give us the specific tangent vector for that value of t along this curve. Okay, so let's take the derivative. We'll have r prime of t is equal to 2t comma 2, right? The derivative of t squared is 2t, and the derivative of 2t is 2. So now, if we plug in 1, we'll have r prime of 1 equals 2 times 1 comma 2, which gives us the vector 2, 2. Okay, so that right there is the tangent vector at t equals 1. That would be the final answer to this example problem, but I do want to show you what that looks like graphically on this plane curve. What you want to do is draw this tangent vector from the point of tangency, right? So we found that the point of tangency, and let's write that down, the point of tangency is 1, comma 2. And for that point, this is a specific tangent vector. So when we graph it, what you want to do is put the initial point of this vector at the point of tangency. All right, so you're going to start at this point and then graph your vector. So in this case, our vector has a terminal point of 2, 2, or in other words, from the initial point, you'll travel 2 in the x direction and 2 in the y direction. So that would look like this. From this point, our point of tangency will move 2 in the x direction and 2 in the y direction. So this would be the terminal point of that tangent vector. And so then you can connect those 2 points and get your tangent vector. That would be r prime of 1. It is the vector that is tangent to that point along the curve. And in this case, since we're working in 2 dimensions, you could also think of it as having the slope at that point along this curve. That's not going to be the case in 3 dimensions because we don't really work with slope. Rather, the tangent vector is just going to tell you the direction at the point along a space curve. But in this case, you could say that for this curve, that this tangent vector also has the slope at that point along the curve. And one more thing that's really cool, something that you want to notice about this tangent vector, and really all tangent vectors, is that they will give the orientation of the curve, right? So the tangent vector is pointing in this direction, right? We started at this point of tangency, and then the terminal point of the vector is over here. So our direction is from here to here, so that's why I pointed this vector this way. That will also point in the direction that the plane curve would be headed. All right, so we didn't really look at this when we sketched this plane curve, but the orientation would be in this direction. If you were to look at a value of t greater than 1, let's say t equals 2, you would have 2 squared, which is 4, and then 2 times 2, which is also 4. So the 0.44 would be for t equals 2, which would be right here. And so you can see that the curve is clearly headed in that direction, just like our tangent vector suggests. Okay, so when you plot a tangent vector, it's going to be pointing in the direction of the orientation of the plane curve. That's a pretty neat little trick that you want to keep in mind. Okay, so I hope this example was a good demonstration of how we can find a specific tangent vector at a point on a vector function using the derivative of a vector function. But let's take a look at another example. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd invite you to join my membership site JK Math Plus, where you get access to many perks including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I will have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. This time we want to find the point of tangency and tangent vector at t equals 0 for this vector function. R of t equals e to the power of 2t times I plus e to the power of negative 4t times j. All right, so just like with the previous example, you don't have to do this, but I am going to draw a sketch of this vector function, or in this case, a plane curve, because we just have an x and y component. I want to draw a graph so you can see visually the tangent vector that we find, but when you do these problems on your own, you don't need to draw a graph. You can simply just find the tangent vector using the derivative. But let's work on sketching this plane curve real quick. Our x component is e to the power of 2t, and our y component is e to the power of negative 4t. So our parametric equations are x equals e to the power of 2t, and y equals e to the power of negative 4t. Now, what we want to do here is eliminate the parameter, which at first seems a bit complicated. How are we going to solve for t in one of these equations and then plug it back into the other one? Well, you could make use of a natural log function and go about it that way, but I think an easier way to look at this is that e to the power of negative 4t is the same thing as e to the power of 2t, but taken to the power of negative 2, right? So you could rewrite y like this, e to the power of 2t to the power of negative 2. Because when you take a value raised to an exponent and raise that to an exponent, the way you simplify it is by multiplying the exponents. So negative 2 times 2t would be negative 4t. So this is exactly the same thing we have right here, just written a different way, and we know that e to the power of 2t is equal to x. So we can just plug that right in and find that y equals x to the power of negative 2, which we could rewrite by moving that to the denominator to get a positive exponent. So y would be equal to 1 divided by x squared. So that's the curve that we're working with here. And we are going to be working with the entire curve, not just a section of it, because if you look at the vector function here, there's no stated restrictions for our values of t, and both of these components are defined for all values of t. You can plug in whatever you want for t here, as long as it's a real number, and you will get a defined x and y component. Okay, so it does look like we're going to work with the entire curve here, although something that you do want to notice about this vector function is that the x component will actually never be negative because e to the power of anything will always output a positive value. So when we do draw our curve, we really don't need to include any part of it that is on the negative side of the x-axis. All right, so we want to take that into account. But let's draw our curve first. And if you remember the graph of 1 divided by x squared, it looks something like this. You have a curve going that way, and then another curve going this way. All right. Neither of those curves will hit the x-axis or y-axis. There are asymptotes along those axes. But as I pointed out before, the x component will never be negative for this vector function, so we don't need to include the curve on the left side of the y-axis. Okay, so that is our vector function r of t, or the plane curve that it represents. Now what we want to do is find the point of tangency and the tangent vector at t equals 0 for this vector function. And so let's start with the point of tangency. To find that, we just have to plug 0 into the vector function. So we'll have r of 0 equals e to the power of 2 times 0 times I plus e to the power of negative 4 times 0 times j. Now, 2 times 0 is 0 and negative 4 times 0 is 0. So for both components, we have e to the power of 0, and anything to the power of 0 is 1. So our point of tangency, or the vector that will give us our point of tangency, is just I plus j. So really the point of tangency is 1, 1. Both the x and y components are 1, so it's a vector with a terminal point of 1, 1. And that would be this point right here if we say that this is x equals 1 and this is y equals 1. So that would be our point of tangency. Now let's find the tangent vector at that point along the curve. So what we have to do is first take the derivative of our vector function. So let's work on that. R prime of t will be equal to the derivative of the x component, and the derivative of an exponential function with a base of e will just be itself multiplied by the derivative of the exponent. So we'll just have e to the power of 2t times 2, right? The derivative of 2t is 2. So that's the x component, and then for the y component, we'll have the same thing, except we're multiplying by the derivative of negative 4t, which will be negative 4. So to simplify what I'm writing here, I'm going to have 2 times e to the power of 2t times I minus 4 times e to the power of negative 4t times j. Okay, so that's our derivative of the vector function. It represents a tangent vector for a specific value of t on that curve. So let's plug in t equals 0 to get the specific tangent vector at that point on the plane curve. So we'll evaluate r prime at 0 and get 2 times e to the power of 2 times 0 times I minus 4 times e to the power of negative 4 times 0 times j. Now once again, both of these powers of e will become 0. Anything times 0 is 0. So we have e to the power of 0 in both cases, which is just 1. So we have 2 times 1, which is 2, and negative 4 times 1, which is negative 4. So we get 2i minus 4j. And so that right there would be the tangent vector at t equals 0 for this vector function. That would be the final answer to this example, but once again, I do want to show you graphically or visually what that tangent vector looks like on this plane curve. It's a tangent vector that has a terminal point of 2, negative 4, but remember, when we sketch these tangent vectors, we're not going to sketch them from the origin. We're going to sketch them from the point of tangency. So that's going to be our initial point. So instead of plotting the terminal point of the tangent vector at 2, negative 4, what we're going to do is measure 2 in the x direction and then negative 4 in the y direction. All right, so starting at that point of tangency, we'll move 2 in the x direction and then 1, 2, 3, 4 in the negative y direction. So this would be the terminal point of that tangent vector. So I'll plot that right here. And then if we connect those 2 points, we'll get a vector like that, which would be r prime of 0. That would be the vector that is tangent to this point along this curve. And you can see that since we're working in 2 dimensions, that vector essentially takes the slope of the plane curve at that point. Okay, so that would be our tangent vector when t equals 0. And one more thing that we know about this plane curve, now that we have sketched this tangent vector, is that the orientation of the curve is in this direction, right? The vector is pointing this way, so we would be heading in this direction along the curve. All right, we're not going this way, we're going this way. A tangent vector will always give you the orientation of the curve. Okay, so that's it for this example, but now you're probably wondering, what about three-dimensional vector functions, right? What about space curves? Can we find a tangent vector at a specific point along a space curve? And obviously, yes, we can do that. But before we look at an example that involves a space curve, I actually want to take things one step further. Specifically, what we can do is use tangent vectors to find tangent lines. Remember from Calculus 1 that using a derivative, we could also find the equation of a tangent line at a point on a function. Specifically, we could do that if we knew two things. We need a point, or more specifically, a point of tangency at x1, y1, and we need a slope, specifically the slope at the point of tangency, which we'd represent with m. Then using that point of tangency and the slope at that point, we would use the point-slope formula to form the equation of the tangent line at that point along a curve. We can do the same thing for space curves in 3 dimensions, but what we need is slightly different, and how we represent the tangent line is also different. In 3 dimensions, we still need a point of tangency, except now it also has a z-coordinate, so we're working with a point x1, y1, z1, and then we need a tangent vector at the point of tangency. All right, because that tangent vector will give you the direction at that point along the space curve. So you would find that tangent vector by taking the derivative of the vector function and evaluating it at a specific value of t, the t that corresponds to your point of tangency, and that will give you a specific tangent vector with components of a, b, and c. Then, once you have the point of tangency and the tangent vector at a point on a space curve, you can find the tangent line by using the parametric equations for a line in 3D space. All right, remember from earlier in Calculus 3 that you can represent a line in 3D space using these parametric equations. X equals a times t plus x1, y equals b times t plus y1, and z equals c times t plus z1. In order to represent a line in 3D space, you needed a point and a direction vector, which is exactly what we'll have with our point of tangency and tangent vector. All right, the components of the tangent vector will be your values of a, b, and c for these equations, and the coordinates of the point of tangency will be your x1, y1, and z1 values in these equations. Okay, so if we're given a vector function that represents a space curve in 3 dimensions, what you want to do to find the tangent line at a specific point along that space curve is to find the point of tangency, find the tangent vector at that point of tangency, and then use that point and that vector to set up a set of parametric equations for a line in 3D space. That line will be the tangent line at that point on the space curve. Okay, so let's take a look at an example. Here we want to find a set of parametric equations for the tangent line at t equals pi divided by 2. And our vector function is r of t equals a vector with components of 2 times cosine t, 2 times sine t, and t. And our values of t are being restricted from 0 to 2 pi. All right, now you can do this type of problem without sketching a graph of the space curve, but to help you see visually what we're doing when we find this tangent line, I am going to include a sketch of this space curve here. We have actually already sketched this space curve in a previous video, so I'm not going to go through all the work again. I'm just going to show you the result of sketching this space curve. It looks like this. If you watched my lesson video on space curves and vector valued functions, then this might look familiar. This specific space curve is contained within a cylinder, and it starts down here with t equals 0 and heads in this direction till we get to t equals 2 pi. All right, and so what we're going to do in this problem is find a tangent line at this specific value of t equals pi divided by 2, which is right here along the space curve. All right, so we're trying to find a set of parametric equations that would represent a line that would be tangent to that point along the curve. All right, and so to do that, remember we have to find two things. We need a point of tangency, and we need a tangent vector at that point of tangency. So let's start with the point of tangency. To find that, we just have to plug this value of t into our vector function. So let's find that. For the point of tangency, we'll have r of pi divided by 2, which will give us 2 times cosine of pi divided by 2, 2 times sine of pi divided by 2, and then just pi divided by 2 for the z component. And cosine of pi divided by 2 is 0, so this will give us an x component of 0. Sine of pi divided by 2 is 1, so you'll have 1 times 2 for the y component, which is just 2, and then the z component is still pi divided by 2. All right, so that would be the vector that would give us our point of tangency. The terminal point of this vector is the point 0, 2, pi divided by 2. All right, so if you want to write that down, you can. The point of tangency is 0, 2, pi divided by 2. But we already have that plotted here. That's this point right here, where t equals pi divided by 2. That is where the x-coordinate is 0, the y-coordinate is 2, and the z-coordinate is pi divided by 2. Okay, so now that we have the point, let's find the derivative of our vector function, because that will give us the tangent vector for that vector function, and then we can plug in our specific value of t to get the specific tangent vector at that point of tangency. And then once we have that, we can set up our parametric equations to represent the tangent line at that point along the space curve. All right, so let's take the derivative here. R prime of t will be equal to the derivative of 2 times cosine t. The derivative of cosine is negative sine, so we'll have negative 2 times sine t. Then we want to take the derivative of 2 times sine t. The derivative of sine is cosine, so we'll have 2 times cosine t. And then finally, the derivative of t is 1. So our z component is 1. So that's our tangent vector for any value of t. But now let's find the specific tangent vector at t equals pi divided by 2. So we'll have r prime of pi divided by 2 is equal to negative 2 times sine of pi divided by 2, then 2 times cosine of pi divided by 2, and then 1. And so sine of pi divided by 2 is 1. So you'll have negative 2 times 1 for the x component. So this is negative 2 comma 2 times cosine of pi divided by 2. Cosine of pi divided by 2 is 0. So this whole component becomes 0. And then finally, we just have 1 for the z component. So this is our tangent vector, specifically the tangent vector at our point of tangency where we want to find a tangent line. So now we have everything we need to set up the parametric equations for the tangent line at that point. Now we just have to put the right information in the right parts of those parametric equations. So here's what that's going to look like. Remember that this is our point of tangency, and this is our tangent vector. And so for the tangent line, we'll start with the x equation. Remember that you'll have x equals a times t plus x1, where a is the x component of the direction vector, right? In this case, our direction vector is our tangent vector. And so the x component is negative 2, and then x sub 1 would be the x coordinate of our point of tangency, which is 0. So we have x equals negative 2 times t plus 0, but we don't need to write plus 0. So we just have x equals negative 2t. Then for the y equation, we'll have y equals b times t plus y1, where b is the y component of the direction vector, or in this case, the tangent vector, and y sub 1 is the y coordinate of the point of tangency, which is 2. So y would be equal to 0 times t plus 2, but 0 times t is 0, so this would just be y equals 2. All right, so that's our y equation. And then finally for z, we'll have c times t plus z1, and c would be the z component of the direction vector or tangent vector. In this case, it's 1, and then z sub 1 would be the z coordinate of the point of tangency. So we have z equals 1 times t, which is t, plus pi divided by 2. And those three equations right there would be the parametric equations for the tangent line at t equals pi divided by 2 for this space curve. Now, it's kind of tricky to actually sketch that accurately, but you can imagine that at this point along the space curve, that a tangent line would cross through the point like this, all right? It's probably not a perfect representation of our tangent line, but you get the idea. It would be a line that cuts through that point of tangency along the curve and takes its direction and extends it forever in opposite directions from that point. Okay, and if you were to try to plot the tangent vector at that point, you would find that it would point in this direction. And so just like with our two-dimensional examples, the tangent vector would tell you the orientation of the curve. And so you would be able to tell that the curve is headed in this direction if you didn't already know that. The tangent vector would point this way, not this way. Okay, so that's the process for finding a set of parametric equations that represents a tangent line to a point along a space curve. I will have more examples of finding these tangent lines in the examples video for this topic, but before we close out this lesson, there's one more thing we need to look at regarding tangent vectors, and that is the concept of a unit tangent vector. Sometimes it might be of interest to find a unit tangent vector or a tangent vector that only has a length or magnitude of 1. And we'll talk more on why you might want to find one of these unit tangent vectors or where they're used in a future lesson. For now, I just want to talk about how we find them, because we are going to use them later on. But the main idea here is pretty simple. Remember from earlier in Calculus 3 that we can find a unit vector by dividing a vector by its magnitude, right? A unit vector u in the same direction of a vector v would be equal to that vector v divided by its magnitude. Or another way you could think about it is that you're multiplying the vector by 1 divided by its magnitude, okay? That will ensure that your vector has a length or magnitude of 1. And so we can apply this same idea to that of tangent vectors, or the derivative of a vector function. We can find a unit tangent vector by dividing a tangent vector by its magnitude. And we will actually use a special notation to represent these unit tangent vectors. It looks like this. For a vector function r of t, the unit tangent vector, capital T of t, is equal to the derivative of the vector function, r prime of t, divided by its magnitude. And of course, this is assuming that r prime of t is not equal to the 0 vector, because if it is, then the magnitude of that vector would be 0, and you can't divide by 0, okay? So as long as your tangent vector is not the 0 vector, then you can find a unit tangent vector. And so to end this lesson video, let's take a look at a couple examples of finding some unit tangent vectors. First up, we want to find the unit tangent vector at t equals e. And so to find this unit tangent vector, we first have to take the derivative of our vector function. In this case, our vector function r of t is equal to 3t times I minus the natural log of t times j. So let's start with that. R prime of t is equal to 3i minus 1 divided by t times j, right? The derivative of 3t is 3, and the derivative of the natural log of t is 1 divided by t. So that's the derivative, or the regular tangent vector, for our vector function. Now, in order to find the unit tangent vector, we also have to find the magnitude of this derivative of our vector function. So remember, to take the magnitude of a vector, you simply take the square root of the sum of the components squared. So this will be equal to the square root of 3 squared plus negative 1 divided by t squared. All right, and so simplifying, we get the square root of 9 plus 1 divided by t squared. Okay, so now we have everything we need to find the unit tangent vector. Remember that it does have its own special notation. We have capital T of t is equal to the derivative of our vector function divided by its magnitude. So we'll have 3i minus 1 divided by t times j divided by the magnitude, which is the square root of 9 plus 1 divided by t squared. So that is the unit tangent vector itself, but we want to find the specific unit tangent vector at t equals e. So let's plug in e and see what we get. We'll have capital T of e is equal to 3i minus 1 divided by e times j divided by the square root of 9 plus 1 divided by e squared. Okay, and really you could leave your answer like that, but I am going to try to simplify it. I'm going to try to make it look a little bit nicer. Specifically, I'm going to multiply by a form of 1. Remember that you can always multiply by 1 because it doesn't change the value of what you're working with. So what I'm going to do here is multiply a form of 1 that looks like this. We'll have e divided by the square root of e squared, right? That is a form of 1 because the square root of e squared is e, and so e divided by e is 1. We're not changing anything here. We're still multiplying by 1, but by doing this, we get rid of this ugly fraction here, and we'll get rid of this ugly fraction here. Multiplying these two square roots will give you the square root of 9 times e squared, and then 1 divided by e squared times e squared is just 1. So here's how I'm going to write the final answer here. Capital T of e is equal to 1 divided by the square root of 9e squared plus 1 times 3e times I minus j. Okay, so I just multiplied e through the numerator here, so e was multiplied by both of those vector components, and then we multiplied the square root of e squared into the denominator. Now, you'll notice I did not multiply the magnitude into the components of the tangent vector. I highly recommend that you don't do that. It makes it a lot easier to work with your unit tangent vectors when we have to use them for other concepts in the future. And so it's totally fine for you to leave your answer in this form where you have 1 divided by the magnitude multiplied by the tangent vector evaluated at the specific value of t. Okay, so it's totally fine to leave it like this. In fact, I would highly recommend that you do not multiply 1 divided by the magnitude into the vector. Trust me, it will make working with these unit tangent vectors a whole lot nicer. Okay, but with that, that is it for this example. And so let's take a look at one more example for this video. For our last example, we want to find the unit tangent vector at t equals 3 for this vector function. And unlike our last example, we have a vector function in 3 dimensions, right? We have 3 components, not just 2. And so there will be a little bit of extra work here because we have an extra component to work with, but the procedure remains the same to find a unit tangent vector. Our vector function here is r of t is equal to t times I plus t squared times j plus t cubed times k. And so if we want to find a unit tangent vector at a specific value of t, we first have to find the derivative and its magnitude of this vector function. So let's start with that. We'll have r prime of t is equal to I plus 2t times j plus 3t squared times k. All right, pretty easy derivative here. The derivative of t is 1, the derivative of t squared is 2t, and the derivative of t cubed is 3t squared. Now let's find the magnitude of that vector. We'll take the magnitude of r prime of t, and that will look like this. We'll take the square root of the sum of the components squared. So we have 1 squared plus 2t squared plus 3t squared squared. All right, and then simplifying, we get the square root of 1 plus 4t squared plus 9t to the power of 4. All right, and then putting those two things together, we can find the unit tangent vector for this vector function. And then once we have that, we can evaluate it at t equals 3. So capital T of t is equal to I plus 2t times j plus 3t squared times k divided by its magnitude, which is the square root of 1 plus 4t squared plus 9t to the power of 4. And then let's plug in our specific value of t into this unit tangent vector. We'll have that capital T of 3 is equal to I plus 2 times 3 times j plus 3 times 3 squared times k divided by the square root of 1 plus 4 times 3 squared plus 9 times 3 to the power of 4. And so simplifying, I am going to move this denominator out front. So we're going to have 1 divided by the square root of 1 plus 4 times 3 squared. 3 squared is 9, so 9 times 4 is 36, plus 1 is 37. So we have 37 plus 9 times 3 to the power of 4. 3 cubed is 27, so then multiplying by another 3 takes you to 81. So we have 9 times 81. And then we're multiplying by the vector I plus 6j plus 27k, right? 2 times 3 is 6. 3 times 3 squared is 3 times 9, which is 27. Then finally, 9 times 81 is 729. So 729 plus 37 gives you 766. And the square root of 766 does not reduce at all, so you can just leave it the way it is. I'm just going to rewrite it right here rather than rewrite the entire vector again. So we'll just have the square root of 766. And that right there is the final answer to this example. That is the unit tangent vector at t equals 3 for this vector function. Okay, it's the tangent vector at that specific value of t that has a length of 1. Okay, and so with that, that is it for this lesson on tangent vectors. If you want to get some more practice working with tangent vectors and all the ways that we did in this video, feel free to check out my examples video for this topic. It will be linked here on the screen. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.